Professor and my dear students, I welcome you all once again to this Railway DNB Anesthesia online academic activities today. Today we have a interesting session and theory question papers and answers will be presented by our students. To start with, I hand over to Dr. Venkateswara Rao from RH Perambur. Over to Dr. Venkateswara Rao.
Yes, sir. Topic is oxyhemoglobin dissociation curve. Sir, sir. Sharing, sir. It's not sharing the screens. Okay, sir. I will present the class, sir. Oxyhemoglobin dissociation curve, also called the oxyhemoglobin dissociation curve or oxygen dissociation curve, is a curve that plots the proportion of hemoglobin in its saturated form on the vertical axis against the prevailing oxygen partial pressure, that is oxygen tension, on the horizontal axis, the x-axis. ODC is a sigmoid shaped curve. Curve is an important tool for understanding how our blood carries and releases oxygen. So ODC relates oxygen saturation and the partial pressure of oxygen in the blood. Determining the hemoglobin affinity for oxygen, that is how readily the hemoglobin acquires and releases oxygen molecule into the fluid that surrounds it. Each hemoglobin molecule has the capacity to carry 4 oxygen molecules. These molecules of oxygen bind to iron of the heme prosthetic group. Binding of one oxygen molecule to one heme subunit causes increased affinity of other heme subunits towards oxygen, which is known as cooperative binding. So as the limit is approached, a very little additional binding occurs and the curve levels out as the hemoglobin becomes saturated with oxygen. Hence, the curve is sigmoid shape or the S shape. This limit occurs at or above PO2 of 60 millimeters of mercury. Coming to the function of hemoglobin is explained in terms of equilibrium between two classical states. First is tense state, that is deoxygenated or unliganded state, which exhibits low affinity for oxygen. Next is relaxed state or oxygenated or liganded state, which has more affinity for oxygen. This T and R state are important because the equilibrium between T and R state are affected by endogenous ligands like hydrogen ion concentration, carbon dioxide, 2,3-diphosphoglycerate that modulate the HbO2 affinity either towards R state, that is left shift of ODC, or towards the tense state or the rightward shift of ODC. From the curve, it is evident that affinity of hemoglobin towards oxygen increases as the partial pressure of oxygen increases until reaching a certain point, that is plateau, beyond which further increase in PO2 will not increase the HbO2. Coming to the P50 value in ODC curve, it refers to the partial pressure of oxygen that is required to fill 50% of hemoglobin with oxygen, which is usually 27 millimeters of mercury. So at PO2 of 27 millimeters of mercury, the hemoglobin is 50% saturated. So in the alveoli, with normal PaO2 of around 100 millimeters of hemoglobin, the hemoglobin should be saturated around 96 to 100%. Whereas at the peripheral tissue, where PO2 is 40 millimeters of mercury, will decrease, which results in release of oxygen from hemoglobin at the peripheral tissues. So an increased PO2 P50 indicates a rightward shift of standard curve, which means that a larger partial pressure is necessary to maintain a 50% oxygen saturation. This indicates decreased affinity. The plateau portion of ODC is the range that exists at the pulmonary capillaries, whereas the steep portion of ODC is the range that exists at the systemic capillaries. So even a small drop in systemic capillary PO2 can result in the release of large amount of oxygen for the metabolic active cells. Coming to the factors that affect the ODC curve. The strength with which oxygen binds to hemoglobin is affected by several factors. These factors shift or reshape the ODC. A rightward shift indicates that the hemoglobin understudy has a decreased affinity for oxygen. This makes it more difficult for hemoglobin to bind oxygen, requiring a higher PO2 to achieve the same oxygen saturation. But it makes it easier for the hemoglobin to release oxygen bound to it. The effect of this rightward shift of curve increases the partial pressure of oxygen in the tissues when it is most needed, such as during exercise or hemorrhagic shock. In contrast, the curve is shifted to left by the opposite of these conditions. The leftward shift indicates that the hemoglobin understudy has an increased affinity for oxygen, so that hemoglobin binds oxygen more easily at the lungs, but unloads it more reluctantly. Coming to the factors which will affect this curve. Coming to the first one, pH. A decrease in pH or increase in hydrogen concentration shift the curve to right, while an increase in pH shift it to the left. This occurs because at greater hydrogen concentration, various amino acid residues such as histidine 146 exits predominantly in their protonated form, allowing them to form ion pairs that stabilizes the deoxyhemoglobin in the tense state. This relationship of blood pH and oxygen affinity is known as Bohr effect. Coming to the carbon dioxide. Carbon dioxide affects the curve in two ways. First thing is formation of carbaminohemoglobin, which stabilizes the T state of hemoglobin. Second thing is formation of bicarbonate, which releases a hydrogen ion into the plasma, thus decreasing the pH. So increase in carbon dioxide shift the curve to right, and decrease in carbon dioxide results in more optical binding condition for hemoglobin, that is leftward shift, which is physiologically favored mechanism, since hemoglobin will drop off more oxygen as the concentration of carbon dioxide increases dramatically, where tissue respiration is happening rapidly and oxygen is needed. Coming to the third thing, temperature. Increase in temperature shifts the ODC to right. As the temperature is increasing, the bond between the iron in the hemoglobin and the oxygen gets denatured, and decrease in temperature shift the curve to left. Coming to 2,3-DPG levels. 2,3-diphosphoglycerate is an organic organophosphate formed in RBC during glycolysis. So any increase in 2,3-DPG has decreased affinity of hemoglobin to oxygen, that is, it shifts the curve to right side, and decreased in 2,3-DPG increases the affinity of hemoglobin to oxygen, that is leftward shift. The production of 2,3-DPG is likely an important adaptive mechanism because the production increases for several conditions in the presence of decreased peripheral tissue oxygen availability, such as hypoxemia, chronic lung disease, anemia, and congestive cardiac failure. Low levels of 2,3-DPG also seen in the states like septic shock and hypophosphatemia. 2,3-DPG, it acts as a heteroallosteric effector of hemoglobin, lowering hemoglobin affinity for oxygen by binding preferential to deoxyhemoglobin. Coming to the effect of fetal hemoglobin and methemoglobinemia. Fetal hemoglobin has a high affinity for oxygen than hemoglobin A, thus withdraw the oxygen from the placenta. This fetal dissociation curve is shifted to the left relative to that of adult. Typically, fetal arterial oxygen pressures are lower than adult arterial oxygen pressures. Hence, higher affinity to bind oxygen is required at lower levels of partial pressure in the fetus to allow diffusion of oxygen across the placenta. Coming to the effect of methemoglobinemia. Methemoglobin is the abnormal hemoglobin where the ferrous has been oxidized to ferric form. This causes leftward shift of ODC, as any residual hemoglobin with oxygenated ferrous ion is unable to unload its bound oxygen into the tissues, thereby increasing its affinity with oxygen. Coming to the carbon dioxide, a brief note on carbon dioxide dissociation curve on how it is different from ODC curve. The carbon dioxide dissociation curve describes the changes in the total carbon dioxide content of blood which occurs with changing partial pressure. It indicates the total carbon dioxide content in the blood. All carbon dioxide in the blood volume present in volume percent is plotted on y-axis and carbon dioxide partial pressure on x-axis. Usually carbon dioxide is transported in blood in 70% as bicarbonate, plasma bicarbonate, 20% as erythrocyte bicarbonate, 5% bound to globin chain as carbaminohemoglobin, and 5% transported in dissolved form. So most of them is transported by H bicarbonate form. The carbon dioxide dissociation curve is more linear and steeper when compared to ODC curve, and it has no plateau. So as the concentration of carbon dioxide increases, the total content of the carbon dioxide increases proportionately. Coming to a note on Haldane effect. Haldane effect denotes a relationship of oxygen affinity and carbon dioxide. That is, a decrease of carbon dioxide binding capacity of hemoglobin with the rise in the concentration of oxygen. Normally, at mixed Venus point, the carbon dioxide content is partial pressure is 46 millimeters of mercury and carbon dioxide content is 52 ml per deciliter at PO2 of 40 millimeters of mercury at the tissue level or the peripheral level. However, at arterial level, the PCO2 is 40 millimeters of mercury at PO2 of 100 millimeters of mercury. Suppose if without Haldane effect, only 50 ml per deciliter will be present at the carbon dioxide content in the arterial blood. However, with the Haldane effect, it comes to 48 ml per deciliter. So more amount of carbon dioxide is liberated because due to increased amount of partial pressure of oxygen, it displaces or destabilizes the hemoglobin molecule so as to release more amount of carbon dioxide, which is a favorable response which usually occurs at the lungs due to Haldane effect. So due to Haldane effect, with the rise in the concentration of oxygen usually occurring in the lungs, will displace the hemoglobin with oxygen, thus liberating carbon dioxide, thus decreasing the binding capacity of the hemoglobin. Thank you, sir. That's all.
Okay. ODC curve, oxygen transport, is a very basic physiology question that often comes in your theory examination. And as an anesthesiologist, in the Viva also, they ask you about what is the peculiarity between the transport of oxygen compared to the transport of carbon dioxide. Now, I have found many students struggling to write this answer because there is little confusion between saturation and partial pressure. That is the basic point that has to be understood to clearly understand and have a clear concept about oxygen transport. Now, when you say saturation, all of us would have studied in our lower classes. The common experiment that the teacher tells you is you take a beaker of water and keep on adding salt or sugar. The initial salt or sugar mixes completely with the water and you don't see any trace of the solid salt or sugar there. And once you keep on adding and there is no more space for it to dissolve further, it starts settling down as a residue at the bottom. At that stage, you say it is fully saturated. That water is fully saturated. That is the common experiment that we have been told to describe about the saturation of a fluid. Here in the blood, the hemoglobin carries the oxygen. All of us know that basic point. And the affinity with which it binds
to the oxygen binds to the hemoglobin, that is described as the saturation. This you can remember by another analogy which I think we can easily remember is like a couple, a man and a woman getting married. So they get close to each other. Like that, the oxygen molecules, one hemoglobin can marry 4 oxygens. Like Muslim law, you can get married to 4 people. So like that, the saturation occurs when 4 oxygen molecules bind to the hemoglobin. Once most of the hemoglobin have been bound to that, we call it that hemoglobin as saturated, fully saturated. And that maximum saturation we can reach is, even though 100% is there, in the majority of the time it is about 98%. So it is the individual binding of oxygen molecules to the hemoglobin is what is called the saturation. But the overall effect of, because every gas has got the property to exert its own partial pressure in a mixture. So that pressure, what you call the partial pressure of oxygen in the blood, not only helps to bind this oxygen to the hemoglobin, but also helps to dissolve it and carry oxygen in the liquid form in the plasma also. So the purpose of this partial pressure is twofold. One is to make the oxygen get attached to the hemoglobin and saturate it, and the second is to make a small volume of oxygen get dissolved in the plasma and be carried with that. So the ODC curve represents the relationship between the saturation and the partial pressure of the oxygen exerting on the blood as a whole. So this is in the, as he said, in the x-axis we plot the partial pressure, and in the y-axis we plot the saturation. The peculiarity about the graph that you plot between these two variables of the oxygen, namely the partial pressure and the saturation, is it is not a linear curve or a hyperbolic curve as you see always when you plot a curve. It becomes more or less what is called the sigmoid shaped or S-shaped curve. The reason for that is there is a peculiarity in which with which the oxygen molecules bind to each hemoglobin. As I said earlier, each hemoglobin molecule can carry 4 oxygen, and when it has delivered the oxygen to the tissues and it is devoid of any oxygen molecule, the hemoglobin is said to be in a state of tense state, that is a closed state. It is not able to take any oxygen. So there is a lot of effort needed for the first oxygen molecules to bind to the site that is available among the 4 sites which are available for binding to oxygen. But once the first molecule of oxygen gets attached, immediately the subsequent molecules slowly open up and start receiving the oxygen molecules much more easily compared to the first molecule, which has to take or break the bonding and all that to open up that molecule and attach itself. This is what is called the cooperative binding. So the first molecule exerts some difficulty in attaching, takes more work to attach itself, which subsequently opens up the oxygen sites which are available and make the rest of the 3 molecules attachment much more easier compared to the second. Third gets attached much more easily compared to the third. Fourth gets attached even more easily. This is what is called the cooperative binding. So that portion of that cooperative binding between the first molecule getting attached to the fourth molecule getting attached, you don't require too much of a increase in the partial pressure. So that is why the curve, when you plot it, it forms what is called a plateau. So initially there is a drop, and then there is a plateau, and then there is a subsequent drop. So that is a safety zone for the oxygen. And that last molecule, once it gets attached, then the saturation will be at about, the partial pressure will be at 60, and then the comparatively the saturation also is at almost 95-94%. Beyond that, once the partial pressure decreases, then the saturation drops very steeply. So this is the peculiarity about that. So even with a partial pressure of 60 to 95 or 80, I mean 98, you can have a normal binding of oxygen with a hemoglobin molecule. That is what it occurs, and that is the safety of our nature, that even when your partial pressure is low, when you go to higher altitude or when your lungs are not working, up to 60, your still the oxygen will be bound to the hemoglobin and will be carried and delivered to the tissues. So that is the peculiarity about this. When you compare it with the hemoglobin, carbon dioxide is not directly attached to the hemoglobin as oxygen gets attached. That is the basic difference we have to understand. As he said, there are three forms in which carbon dioxide is carried. The majority is carbon dioxide because it can easily dissolve in water. It forms carbonic acid, which is not a stable acid. It's a weak acid. So there is an enzyme called carbonic anhydrase, which will immediately act on the carbonic acid and break it into hydrogen ion and bicarbonate ion. The hydrogen ion has a positive charge and bicarbonate ion has a negative charge. So the negative charge of the bicarbonate will make it shift to the plasma, and chloride will be replaced, which is called the Hamburger phenomena. And this is the main form. The bicarbonate form is the main form in which carbon dioxide is transported from the tissues to the lung level, from where it is exhaled outside. So that is the reason why the proportionate formation of carbon dioxide determines the value of your CO2 in the body. So the curve, when you plot, it goes as a linear curve. It is not a S-shaped curve like your ODC curve. So that is the basic difference that you have to understand. And factors which shift this curve from the normal position to either right or left depends on various factors, as he mentioned. And I always tell students to remember easily, if the oxygen dissociation curve shifts to the right, it is good for the tissues. It is right for the tissues because oxygen will be easily dissociating from the hemoglobin attachment to go into the tissues. On the contrary, if the oxygen dissociation curve gets shifted to the left, then the oxygen is more firmly bound to the hemoglobin and it is not easily released from the binding, and tissues will not receive adequate oxygen. So shift to the left is bad for the tissues, shift to the right is good for the tissues. So whenever there is a demand or situations which warrant more release of oxygen, like acidosis, like hyperthermia, like increased CO2, in all these situations, body wants to restore the normalcy. So you have to give more oxygen to the tissues to continue with the aerobic metabolism and prevent anaerobic metabolism. So naturally, if you know this basic concept, you will be able to understand why the shift occurs to the right and why it goes to the left in some conditions. So pH decrease, acidosis will always shift it to the right because you want more aerobic metabolism and not anaerobic metabolism. Whereas if it is shifting to the left, that means there is an alkalosis. So that's a washout of carbon dioxide. So you want more uh, hydrogen ion to accumulate to bring back the pH to normalcy. So there is a less release of oxygen. So even if you have anaerobic metabolism, that is good to restore the pH to normal. So acidosis shifts it to the right to maintain normal pH. Alkalosis shifts it to the left to inhibit the anaerobic metabolism and allow accumulation of hydrogen ions to restore the pH. So ultimately, it is the aim with which that is working. And similarly, about 2,3-DPG he described, it is a byproduct of glucose metabolism in all the cells. It is not only in RBCs, but it is all the cells produce this 2,3-DPG as a cytosolic step in the glucose metabolism before they go to the mitochondria ultimately as pyruvate. So in the RBCs, what happens? This 2,3-DPG also has an affinity for the hemoglobin molecule. So when the 2,3-DPG value is high, it will not allow the oxygen. It will compete with the oxygen for the site and prevent the oxygen getting affiliated or affected to the attached to the hemoglobin and cause more release. Whereas when the 2,3-DPG value is low, then oxygen will have more space to attach itself to the hemoglobin. So it will automatically attach itself and less oxygen will be released. So these three factors, pH, temperature and 2,3-DPG values are very important in determining whether the curve has to be shifted to the right or to the left. So if I show you just a graph and then explain this, I think that will be more easily understood than just describing by words. Visible? So see, this is the PO2, partial pressure of oxygen, which is marked from 10 to 100. That is the maximum that you can achieve. And here the saturation, which is also maximum 100. So when you are asked to write about this in your theory paper, first thing you draw a graph with an x-axis and y-axis. Both of them you make a marking of at intervals of 10 to a maximum of 100 on the x-axis. Similarly, calibration of 10 up to a maximum of 100 in the y-axis. Y-axis, we always say it is the oxygen saturation percentage, and the x-axis always partial pressure of oxygen in millimeters of mercury. So what happens when you start with zero pressure? There is no saturation. As I said, there is no pressure to make the oxygen get bound to the hemoglobin. But as you reach here at a pressure of 60 millimeters of mercury, if you plot the graph, then this even at 50 millimeters of mercury, it is almost 84-85% saturation is there. But after that, below that pressure, it starts dropping, the saturation starts dropping. And after that, 60, 70, 100 millimeters, the maximum you can reach is about 98% of saturation. So that is the first thing. This thick blue line is a normal one which you have to draw. Then when you start drawing the shift to the right, this is the red dotted line, where you will find the release is much more. When even in the pressure is little 60, you find the saturation is almost again 85, and when it is shifted to the left, this green dotted line, you find even at 40, it is almost 85. That means it is holding on to the oxygen more. Whereas here at higher pressure, it is releasing. So the three factors which control the shift to the right or left is, the shift to the right is maintained by low pH, increase in 2,3-DPG, and increase in temperature. On the contrary, shift to the left is by increase in pH, that is alkalosis, decrease in 2,3-DPG, and decrease in temperature. So this is quite easy to draw. Once you draw this, even these lines you don't have to draw, you just have to draw only these three lines, shift to the right, shift to the left, and remember how to label them. PO2 on the x-axis and oxygen saturation on the y-axis. Then always you remember about the sigmoid shaped or S-shaped curve, and this is the plateau that is happening after from the initial pressure. Up to this, it is almost 85% saturation is there. After that, only it starts dropping. So even if you are able to achieve a partial pressure of 50 to 60, your saturation or binding of oxygen to the hemoglobin molecule will be quite adequate for the tissues to receive oxygen. But when the PO2 value goes down below this, then only the whole problem happens and the binding itself becomes difficult. So oxygen carrying will be very much reduced. Now coming to the carbon dioxide curve, again in the x-axis, here you just make the PCO2 value. Just as you mark the PO2 value here, you have to mark the PCO2 value and the carbon dioxide concentration, that is ml per deciliter. These are the two things that you have to mark here. You can forget about this line, which is mentioning the values in different formats. It is in millimoles per liter, here ml per deciliter. So you can easily forget this and just draw these two lines. And if you see that there is a dissolved portion which is gradually increasing as the pressure increases. Then there is a portion which is the difference between the arterial and venous. The carbon dioxide levels in the arterial blood and venous blood are slightly different, as you all know. So venous blood is the main one which has to carry all the carbon dioxide back to the lung. So that is where the Haldane effect comes in. Haldane effect is nothing but the mechanism by which the carbon dioxide at the lung level is made to get eliminated. So that you have to remember this the Haldane effect. Whereas at the tissue level, we want to deliver more oxygen to the tissues, and that is what is called the Bohr effect. Bohr effect and Haldane effect, both are the interrelationship between the oxygen and carbon dioxide at different levels. At tissue level, the oxygen gets released to facilitate removal of carbon dioxide from the aerobic metabolism that has happened at the cellular level. That is Bohr effect. Whereas at the lung level, the oxygen is taken up and carbon dioxide is released towards the alveoli for its exhalation, which is called the Haldane effect. So Haldane effect and Bohr effect are nothing but the interrelationship between the oxygen and carbon dioxide. Bohr effect at the tissue level, Haldane effect at the lung level for elimination. So this is how these two are compared. The Haldane effect describes how oxygen concentration determine the hemoglobin's affinity for carbon dioxide. So this is how it will make more oxygen to be bound to the hemoglobin and release the carbon dioxide for elimination. Whereas at the Bohr effect describes how carbon dioxide affect the hemoglobin affinity for oxygen, that is at the tissue level. So more carbon dioxide causes release of oxygen into the tissues and it binds and comes to the lung level. So these are the two things, and this handwritten note tells you the comparison between that. So Bohr effect, when blood reaches the tissues, what happens? In the tissues, there is a higher pressure of partial pressure of carbon dioxide is more because of the aerobic metabolism, and also carbon dioxide mixes with water to form carbonic acid and causes breaks down into hydrogen bicarbonate. So therefore hydrogen ion increases, there is a decrease in pH, which will cause a shift in the ODC curve. So oxygen will be easily dissociated, Hp and O2, oxygen released and sent into the tissues. Whereas in Haldane, when the blood reaches the lungs, the lung CO2 partial pressure is more. So the carbaminohemoglobin dissociated into Hp and CO2, and CO2 is sent into the lungs for expiration. So Haldane effect is the effect of oxygen and carbon dioxide transport, whereas Bohr effect is the effect of CO2 on oxygen transport. So how these two are interconnected is what is to be understood. So remember Haldane at lung level. There is a L in that Haldane. So you remember it is the lung. In bore, it is the opposite tissue. So that is how you can easily remember that. And I think that should be enough to describe about this. Any doubts or any questions you want to ask?